Next speaker is our Professor Hiroyuki Iizuka, and the title is the Shared Module Neural Network for Self-Other Differentiation and Symbol Grounding. So please.
Okay, thank you. And I'm Hiroyuki Iizuka, and today I'd like to talk about our proposing the shared module neural network. And then I want to talk about the two topics if I have a time, and it's going to be a very challenging, I know. But one is about the multimodal integration and symbol grounding, and another one is the self and other differentiation. And usually in multimodal integration, the problem is how to integrate the information coming from each modality in a mixed way. And the brain tries to extract the integrated information from them. And usually it can be very complicated. But our objective of this talk is that introducing a simple neural mechanism that enables multimodal integration and showing the consequences of having the mechanism in the brain by a simulation-based synthetic approach. That is the objective today. And first, let me explain the simple neural mechanism called a shared module neural network, modeled by the deep neural network. And this figure shows the basic structure of the shared module neural network. And the neural network receives the sensory inputs from each modality and predict the future sensory inputs. Each modality has a different encoder and a decoder to process, but they share this recurrent neural network module to predict. And then this can be a kind of a constraint for learning. And then this also illustrates how the model works. And the important thing is that those connections are not the usual integration, but those transform the feature vectors are interchangeable between among the different modalities. So the shared module has just a fixed number of input nodes, the 64. So all these transform the feature vector as the 64 dimensions. And then sometimes this is interchangeable, and then sometimes the shared module receives the vision feature vectors, and then sometimes from the hearing, and sometimes from touch. So again, the important thing is that they're interchangeable. So sometimes get the vision and sometimes get the hearing, and then shared module use the same input nodes for those inputs. Okay. And then the shared module neural network is implemented in this agent, and this agent moves around the environment, and the shared module neural network predicts the vision, audio, and the tactile sensory inputs. And the environment consists of a two-dimensional arena, and there are 4 visual landmarks at the corner, and 4 audio sources, and 4 bumps areas evoking the sense of touch. And then this is the example of the visual inputs, right? And then this is the hearing, and then this is a touch. And the hearing and touching have a different spatial intensity distribution like this. So there are 3 kinds of senses. And all the shared module neural network has to do is just a prediction of future sensory inputs, right? And then loss function is given by the mean square error, like this. This is the prediction, and this is the actual sensory inputs. And then try to minimize these differences. And then the feature vectors sometimes are blocked by the mask function. So when the inputs are blocked, prediction has to be performed by the memory alone, this memory alone. Okay. And then this is a result of the vision prediction. And after the learning, so this is the ground truth, and then the shared module neural network can predict the future vision inputs like this, right? This is the performance, looks very good. And then next, we try to visualize the internal state of the shared module neural network. then internal states at each time step are plotted with points on the ICA space. And the color of points shows the position of agents at that time. So in this case, for example, this internal state shows that when this agent is close to the red landmarks, then the internal state was here. And then when this agent is close to the yellow landmarks, the internal state is here. So as you can see, the two-dimensional internal states are self-organized in the shared module neural network, and the dimension is corresponding to the spatial dimensions of the environment as well. And also those internal states are maintained in the correspondence with the physical location as well. So this is very close to the place. So this internal state shows the corresponding to the actual position as well. Okay, and then this is a result of the hearing prediction. This is the ground truth, and this is a prediction. So that agents can properly predict the hearing information as well. And the touching, this is the result of touching. So touching is also can be properly predicted like this. And then again, we try to visualize the internal states of for the hearing and touching as well. And then the same in the same way, the internal states are plotted with on the ICA spaces, right? And then you can see, as you can see, the internal states are maintained in response to the physical location again, and then even with the tactile and auditory sensations, so form the similar structure with vision. And then reusing the two-dimensional structure of spatial representations by vision, and also the consistent spatial representations are formed over different modalities to conform to the common motion sense. So motion is they're always same. So because the shared module neural network tries to keep the consistency among the sensor modalities, and then they just try to create the same spatial representation among the vision, hearing, and touch. So by having a shared module mechanism, a single common representation is naturally formed in the shared module neural network, right? And then we apply this neural network to map reading as understanding the external symbols. So this is the map view. And then imagine the situation like this. So the people were watching the map and then try to point out the current location with the fingers and then moving around. It's like a virtual walk on the map and then moving around, and then the figure is moving like this. And then we use this map input for the shared module neural network. This is the current model of the shared module neural network, but we just give this map input to the shared module neural network. And then this shared module neural network have the specialized, for the map input, the shared neural network have a different encoder and the decoders. And also this map, the motion is not related to the actual motion, the moving forward, the moving back. So it's not related to the actual motion. So we introduced the virtual motion generator here. And then all the shared module neural network has to do is just a prediction of the map prediction, this one, right? And then this is a result of prediction. So using the shared module neural network, the prediction is properly performed like this. And then at that time, we just visualize the internal state again, and then see for the map prediction, the internal state is self-organized in two-dimensional space, but there is no consistency between the vision and the hearing and the touching. So it's not a consistent spatial representation. So again, the sharing using the shared module neural network, they can share the two-dimensional structure of spatial representation. but the location is not consistent. So the map representation is not grounded in the physical space at the moment, right? So that we introduced the matching loss for grounding map representation. So just we give the teaching signal to create the association between the map and the physical location. So this point and this point must be close. No, that is the teaching signal. And the loss function is just the distance between this one and this one that try to minimize this distance in the internal states. And then matching loss is actually given to the only 4 locations. And then this is the result. Without the matching loss, the internal representation is not corresponding to these one. But with the matching loss, actually the internal state corresponds to the other sensor modalities. So spatial and map representation coincides even in non-trained location. And then we try to analyze them, the virtual motions. Then in order to use the same spatial representation for the shared module, the virtual motions are also self-organized to match the actual motion. So the map representation are grounded by matching a spatial representation and giving an interpretation of actual motion to virtual motion. So actually the virtual motion corresponds to the actual physical motion as well. And then by doing this, the map representation can be grounded on the physical space. And also we can just apply this system to the navigation as well. And I don't explain so much, but the agent can go to the location indicated by the map, because the map representation and the spatial representation is a shared. That's why it's possible. So in the end, by giving the matching loss, the map representation can be grounded on the spatial representation. That's my conclusion. I'm sorry that I just took time. So actually, if we use the shared module neural network, the multimodal integration, symbol grounding, and self-other distinction can be performed. And actually, we found the neuroscience scientists found the kind of the evidences for the shared module neural network. So I think we believe that the shared module neural network somehow exists in our brain. That's my message. Thank you so much.
Thank you very much, Hiro. We have time for questions. Please raise your hand or just speak out. Martin.
Yeah, hi, can you hear me?
Yes.
Yes.
Okay. So when you showed these IC components,
yep,
somewhere pretty much in the beginning, I didn't get, how do you, yeah, so how do you get so this is, I guess it's independent component?
Yeah, yeah.
Yeah, so how do you get I thought there's a shared module, so there's only one state, so it only has one independent component. But how do you get different ones?
Okay, actually to get the components, we use the vision, for example, vision data. So with the internal states, when the agent use the shared module neural network use the vision sensor, and then we create the ICS space, and then we plotted the internal state on that space for vision, and then using the same space, we plotted the internal states for the hearing and touching as well.
So so you're doing it when it's using vision. How does it?
When?
Like how do you? I still didn't get it. How do you force it to be about vision? Like how do you force the internal state to be about vision and not about hearing when you get the IC1?
To get the IC space, we all just keep giving the vision input to the shared module neural network, and then create the space. And then we apply next time we give the hearing sensory inputs to this neural network, and then we just stores the internal states and then plotted the
Okay, so
those intercepts on them.
so it's kind of conditioned on the input coming from vision, or conditioned on the input coming from hearing.
Yeah, exactly. Yes.
Okay. Okay, because yeah, it's kind of it's a bit interesting, because this is kind of, it's a little bit like an interpretation map. What Nathaniel talked about, the interpretation map of Nathaniel, like, because now you're interpreting the internal state of this shared module as a kind of vision, like as a kind of vision representation. But it's a bit more subtle, I think. So I have to think about it. Yeah.
Yeah, actually, those internal states are model of the real world.
Yeah, exactly.
Because the network is just always keeps the predicting to the future state and then try to create the internal model in the internal states. Yes, thank you.
Yeah.
Any more questions? Elana.
Yes. The mismatch between the different modalities without the matching loss reminds me a little bit of motion sickness. Like, some people say that motion sickness is when your visual input is not corresponding to your motion motion sensation. Do you think there is any kind of link here, or is it completely different?
Yeah, I think motion sickness is caused by the misintegration of the sensory inputs, from the vision and also from the proprioception. If they have a dichotomy or the differences between them, I think the motion sickness can happen, usually. Mm-hmm. So in this case, actually, I don't know if it's related to motion sickness, but actually the representation created by the map prediction is not consistent with the representation created by the sensors, the physical sensors. So they have the dichotomy between them. So in that sense, if try to understand the actual motion with the map representation, then in that sense, the motion is maybe confused and can be a motion sickness or something. I don't know. Yeah.
Thank you.
And Takashi.
Well, my question is very the basic. I just want to confirm. For example, in this page that you said, GEN is for generator, right?
Yeah. Yes.
And in order to get, is this like a fictitious motion or something that should be input into the shared module?
Yeah.
In order to have the consistency between the actual physical state and the way you're working, right?
Yeah, that's right.
So how you can construct this generator?
Yeah, actually, it's a bit complicated, but actually, we give the two visual images, the consecutive two visual images. So time t and time t+1 to generator, and then this generator understands what the agent moves, and then the result is going to the shared module. But actually, we don't give any teaching signal for the motion. That teaching signal is just a prediction of the visual inputs. But in order to share the spatial representation here, the motion is the self-organized to match the actual motions.
I see. So this is the only. Well, actually, what I want to know is that there like a speed. So the behavior should be. This one is a random behavior, right? But the behavior.
Yeah, actually, yeah, given sequences, yes.
So I see. So this random behavior, the actual physical moving tracking is replicated by the generator over here, right? And so this one is constructed from other algorithm, or is this just self-organized when you put this generator network attached to the shared module, and then they just do this experiment so that the generator is self-organized from this input and output?
Yeah, that's right. Self-organized.
But there's no teaching signal here.
No. But using the spatial representation, they keep the consistency between the inputs and outputs. So this motion vectors should be close to the actual motion, because this network is trained by the actual motion. And then so this vector will be
I see.
yes, organized.
Thank you.
And then we just this is kind of building interpretation of the virtual motion with the actual motion.
Thank you. I have one short question. I'm not quite sure how much the multimodal shared network is crucial. What if you train the network only with vision or vision and touch to map the, I mean, you train the network first with the 3 modality, but if you do only with vision, the network still run the map on?
Yeah, actually, with the only vision, the network can create a spatial representation like this. But I think the spatial visual information have a lot of information to estimate the current location. But with the hearing and the touch is a bit less information, so it might be difficult to create a spatial representation from these kind of sensors. But I think it can be possible. It's possible.
Okay, thank you.